Okay, so again, we are going to wrap up binary search trees today. I want to first start with going over how to code a traversal. We'll pick one of the 3 traversals and code that one. This is something that you guys need to do for your programming project. You have to do all 3 for yours. So we'll code one of them just so that you can kind of see how it works. And this will give you a starting point for how to do it in yours. You'll have to modify it slightly because you guys are putting different objects in yours. But the same algorithm or process is going to be the same. Okay? So we're going to take care of that, and then I'm going to open it up for any questions that you guys have about your third programming project, things that you might be stuck on, things that we can kind of give you a little nudge in the right direction to keep you moving on that. Okay? All right, so what I've got is our programming or in-class program pulled up here. This is our Pop-Tarts that we've been working on. And the current version is posted to Canvas, so you guys can check this out. As soon as we finish this today and add the traversals to it, I will post that on Canvas as well, so you guys have access to this code. I'll also post this video so you guys can reference that as well. Okay? So, just a quick recap to what we do. We're adding 20 Pop-Tarts to our binary search tree. The ordering value that we have for our Pop-Tart objects is a calorie that is randomly assigned when the Pop-Tart object is created. That's how we use, but that's the determining factor for how we sort them. And then we go through and we search for three random calorie values to see if it's in there. Okay, so this demonstrates 2 of the 3 things that you guys need to do for your programming assignment. You need to be able to properly add to the binary search tree. In your case, you're going to be adding string objects wrapped up in a node. And the other thing that you need to be able to do is search your binary search tree to see if a particular node object that contains a specified string exists. All right, and the third and final thing you have to do is traversals. Okay? And you have to call 3 traversals, one after another. Do me a favor, when you are doing that in your program, it doesn't specifically say to do this. When you call the traversal method, output in the traversal method just a very brief message that says, hey, I'm running pre-order traversal. Hey, I'm running in-order traversal. Just so that we can see them. Otherwise, what we're going to get is like 90 words that show up all one after another. Okay? So just segment it so we can see what's being called. Or even if you put a couple lines in between, just make it a little bit easier to read your output. Okay? Okay, so we search for those 3, and then what we want to do is we want to call a traversal method. Okay? And so if we go back, what I'm going to do is I'm going to open up your driver. So this is what you have for your third programming assignment. I got a couple questions about this. What these numbers mean. Okay? I covered this when we went over the very first day what this stuff, or how to use this. But it was a lot of information, so let me cover it again. You don't need these. This is an optional thing for you. Okay? You can run this as is, or again, you don't need to make any changes to your driver in order to get it to work. The reason these exist is because if you try to run this in the Canvas, these words aren't going to show up inside of the little circles that are created in the Canvas when you're JGrasp. Okay? I think you can only fit like 2 characters. And so it's going to be difficult to see. And so what these numbers do is they are just an alternative to using the words. You'll notice that there's the same number of words as there are string numbers. Okay? And this is just so that you can see the contents of it inside of the Canvas window. That's the only reason this exists. Okay? It's just an alternative. You don't have to mess with it at all. It's just if you're using JGrasp and you want to output it in the Canvas window and you want it to be a little bit easier to read. That's all. Okay? So this takes care of adding. And then at the very end, right here, you'll notice we call tree dot, and then print pre-order, print in order, print post order. This is where they're called here. Okay, one after another. And that's what we're going to do in ours today. So I'm going to go to driver, and we call this Pop-Tart tree. So I'm going to say Pop-Tart tree dot print pre-order. We're just going to call it. Like call print pre-order. Okay. If we go over to binary search tree, we have an add and then we have the recursive add. We have the search and then we have the recursive search. And down here, say public void print pre-order. This is what I was talking about. Have a simple message inside of your print pre-order that says, we'll say, running pre-order traversal. That's it. Just something simple. Running pre-order traversal. And then it's going to spit out all of this stuff. Okay. Now, if you remember, pre-order traversal works by what procedure? What's the order? Root, left, right. Good. And when we're talking about left and right, we're talking about left subtree, right subtree. So each time we say left or right, that's a recursive call. We are dropping down to another level of the tree, making a new subroot. Okay. So when we start this, and you guys hopefully can see kind of a pattern. There's always an initial call, and then there's a recursive call after that. We had an initial add method and then a recursive add method that repeated. We had an initial search method and then a recursive search method that was repeated. Okay? Initially, when we were searching, we specified a calorie value, and then the recursive search, we specified a calorie value in addition to a subroot. Same thing with adding. We specified what we wanted to add in the initial search. We specified what we wanted to add in the recursive search in addition to the subroot. So when we're talking about doing print pre-order, we're going to do the same thing. Okay, we will start, always our traversal start at the root. So we're going to start at the root. Okay, so let's get our initial call going. We can say print pre-order, specifying that we want the root to be the first variable. We'll say void print pre-order Pop-Tart. Was it capital T? I don't remember. Yeah. Pop-Tart subroot. See how that works? See the pattern? Here we don't pass anything. In our search method, we pass the calorie value. In our add method, we pass the Pop-Tart object that we wanted to add. But when we call print pre-order, we didn't pass it anything because we wanted to do the same thing every time. Visit all of the nodes in pre-order order. And starting with the root. So when we call print pre-order, the recursive version, we have to specify the subroot that we want to do. Every time we call print pre-order again, the next time we're going to be passing it the left child as the new subroot. And we're going to continue the process. Okay. Now, every recursive method has to have what? What's it have to have? Has to have
a base case.
Has to have a base case. Very good. If it doesn't have a base case, what happens? Yep, goes on forever and ever and ever. Infinite recursion. So, what is a base case? You can define what a base case is.
It's one that ends a method, or it's a statement that can end a method.
Okay, good. So it's a statement, a condition, that ends a method. Specifically, it ends the recursive calls in a recursive method. Okay? When the base case occurs, no more recursive calls are made. Stops the recursion. So we know if we've got a big binary search tree, and we're going through and we are traversing it, meaning we're visiting every node in a specified order, we're going root, left subtree, right subtree, root, left subtree. That process continues until what happens? At what point do we say, stop making recursive calls? And so let me ask you one more question. Let me give you a little bit more information. It starts, and what is the first node that we visit? The first node that we print out in pre-order traversal. The root. Because it goes root, left subtree, right subtree. So if we look at the initial, grab the marker. Deciding whether it's better to draw it up here. Let's see if I can draw this. So let's say we have a sample binary search tree that looks like this. Okay. We call pre-order traversal. We call pre-order traversal, and we specify that we want to look at this first, where our subroot is this guy. That's the root of the tree. We keep a permanent reference to the root of the tree, and we pass the recursive print pre-order method the root of the tree, and we specify that's our current subroot. Our initial subroot is that. So we always have access to 3 nodes in a binary search tree, and we're starting our subroot out as 19. Okay? Now, it works like this. Root, left subtree, right subtree. So the first thing that we're going to want to do is we're going to want to call our toString method on our subroot, correct? All right, so we're going to say subroot.toString. Always. Now, what happens if our subroot is null? Is that possible? Is it possible for our subroot to be null?
It's possible,
Possible for our subroot to be null. Based off of how we have it set up.
If the root is null.
If the root is null, if the tree is empty, we're in trouble. We're going to crash. Okay. So we need to check to make sure that that's not the case. That ensures that it's not null. So we could do it that way. Make sense? We could also do it this way. Questions? So if we get here, print root. So we'll call it print the subroot. Subroot dot toString. So we need to wrap this inside of system.out.string. Whoop. System.out.string. Subroot.toString. Left subtree. Now, when we had this a minute ago, when we were here, we did. That's not what I want. Don't be stupid. But I can't erase it. Okay.
Use the backbone.
Ah. I win. Okay, so we did this. Subroot.toString. Now, the next thing we want to do is we want to do the left subtree. So whenever we see subtree, we know that means a recursive call. So now we're going to look at this. So we need to set subroot to be this guy. And this is a new recursive call. So now we are going to call preorder traversal again, specifying this as the new subroot. So how do we do that?
You have to make the left child the actual subject.
Does that work? Okay. What if there's not a left child? No. Subroot.getLeftChild. If there's not a left child, what's that going to result in? Null. So we pass null to print preorder. If subroot equals null, return. Works pretty well. Now, if we, remember how at first we had the, if root does not equal null, then do this? If we have that up there, then right here what we have to do is say, if subroot.getLeftChild does not equal null, then do it. Okay, this is more elegant, because then we don't have to check it over and over again. We do it the other way, we have to check it here, we have to check it before we call the left child, we have to check it before we call the right child. Here it just does it all at once. Okay? Prefer this one. What goes here?
Same thing except right child.
Yep, same thing except right child. Copy paste is friend. Is that it? Very easy. That'll do a whole tree. That'll do a whole tree. Let's run it, see if it works. Go to our driver, compile, see if we got any errors. Yeah, didn't like something. Not good at capitalization. but I was supposed to capitalize those. So let's run this in the canvas. I'm gonna let it go real fast. We had what, 20? A lot. I'm going to stop it. Let's just do 10. And I'm going to comment out our searches. We know this works. All right, good. We're going to get a bad treatment. You can answer. Well, we'll talk to him. You okay?
Excuse me. I'm gonna die, but it's okay.
You're going to die when you step out.
We don't even know about
There's a
that
lot of red tape when somebody dies in the classroom. Nobody likes paperwork. But you're okay then.
Yeah, thank you.
Okay, so we're running pre-order traversal. I don't think I caught it. No, that's okay. And so let's take a look at what we've got. Well, I think we're actually backing out. Okay, we're backing out of the admin. Okay, so we call print pre-order. Let's find out if this works. So we're paused right here. We're going to call print pre-order. There's our tree over there. Notice the only node in the tree that we have access to directly is the root. We keep a permanent reference to the root of the tree in that variable. Okay, so we're going to go in here and we call print pre-order. So we can look down here at our output window down at the bottom. There's our console, and it says running pre-order traversal. Okay, that's good. So the first thing that we do is we call print pre-order on the root, which is 1017. Done. Now, notice that subroot and root both reference the same thing. Okay, because our subroot, we want to start at the root of the tree. Okay? So the check is, right here. The check is, give me 1 second. Okay. The check is, the first thing we do is we call, or we have to first check to make sure that the subroot's not null. Is our subroot null?
No.
No, it's not. It actually points to an object. It points to 1017. Okay, so that's going to be false. So we skip down and we output the root. We output the subroot, that's 1017. We call its toString method, and we print it out. So it shows 1017 right here. Okay? Then the next thing that we do is we do the left subtree. So this doesn't mean print out 1010. It means do a recursive call on the left child. Okay, so look over the floor. So we're going to call subroot.getLeft, grab the left child, which is 1010, and we're going to pass that to the recursive print preorder method. So we do that. Notice now subroot references 1010. Okay, so now we've moved the process down here. There is still a print preorder method with subroot being 1017 on the stack. It's just on hold. Okay, we'll get back to it later. So now we're here, and the first thing we're going to do is make sure that subroot actually points to a child. Because it's possible that 1017 didn't have a left child. If it were null, this is where we would break out. This is our base case. Okay? So, it does equal an object 1010, so we're going to print that out. So we print out 1010. Next thing is, does it have a left child? We're going to call it on the left child. So we grab the left child, and we continue the process. Now it's down at 1006. 1006 is not null, so we call its toString method, and we print that out. Okay? Grab its left child. It's also 1006. It's not null, so we print it out. Do the same thing. This process is going to continue on and on. 1004 is not null, so we output it as well. We can see it just continuing to output down here. Now, we call print preorder. Remember, subroot is 1004 right here. Notice it's pointing right here. So we're going to call get left child of 1004. So we call get left child, and we take that and we pass it to print preorder. Notice now subroot is what?
No.
It's null, because 1004 doesn't have a left child. And so at this point, we have reached the base case. No more recursive calls, at least on the left side. Okay? So we're going to return. Watch what happens. Now when we return, we go back, so we hit the return statement, and we go back to where subroot was 1004. So we went back up a level. We returned to the previous recursive call where we initially had called print preorder down the left side. Okay? We ended there and then we returned back up here. What's the next thing that we do? We go down the right side now. Okay? So we're going to call print preorder get right child. So we get the right child of 1004. Got it? We're called print preorder on that. There is no right child, so subroot is null. We're going to hit the base case for the second time, and we return back. Okay? Now, at this point, subroot is 1004. We have gone down the left side. We have gone down the right side. And now we end. And when we end, we immediately go back up to the previous method. And when we go back up, the previous method was when the subroot was 1006. Good? So now we're up. Subroot is 1006. And notice now we are right here. We have already output 1006. We've gone down the left side of 1006. We've gone down this way. Now we're going to go down the right side. So we're going to call subroot, which is this one, dot get right child. So we get the right child, come back here, call print preorder. Notice subroot is null because 1006 does not have a right child. So we return back to where we are here. So we notice right now the arrow shows where we are. We have now finished this method because we have printed out the root of 1006. We have gone down the left side of 1006, and we've also gone down the right side of 1006. So we're going to return back up to here. Okay. Same thing's going to happen. There is no right child. Okay. There is no right child of 1006. So when we return, we're going to go back up to 1010. Now, in this case, we're up at 1010. We have already printed out the root of 1010 here. We have gone down the left side, exhausted all of this. Now notice where we are right now. We are on print preorder doing the right child. So we're going to say get the right child of 1010. We do that. The right child of 1010 is 1012. So notice now the subroot is 1012. Check the base case. Is the subroot null? It's not. It's 1012. So we skip that and we print out the root, which is 1012. Notice it'll show down here. So we call the toString method, and it shows down at the bottom right now. So it outputs 1012, and then we check left child, right child. There is no left child, so we call get left child. It's null. Subroot's null, so we return back. Then we check the right child. It's null. Return back. So now that we finished that, we return back to 1010. When we return back to 1010, it immediately kicks us up to 1017 because we finished that. So we have now gone down the whole left side. We started with 1017, we did 1010, 1006, 1004, 1012, and now we're going to do the right side of the tree. Okay? Just going to let it play. You can see it finishes. This is preorder traversal. Do you want to do one more? We'll do all. Let's do in order, because that's, for binary search trees, that's pretty useful. So we'll say pop tart tree dot print in order. Who remembers in order? Left, root, right. Okay. So here's what I want you to do. Take 3 minutes, rearrange this code to give you left, root, right. Okay. Rearrange this code to give you left, root, right. Yes. Sure. What's up? Use the go-to method in class.
It automatically does it.
Yep. Yep. All right, so let's talk about this. If you aren't finished, it's okay. Who's got a solution? Is it really simple? Go ahead.
Is it just re-switching print subroot left tree, right tree into left, subroot, and right?
Is it as simple as just switching these 2 lines of code? Let's find out. Let me condense this just a little bit. Copy. Paste. So we'll call this print in order, running in order, traversal, print in order, print in order. Subroot's null, do that. I'm going to comment out for print pre-order.
You're going to have to change some of the print in order.
Yeah. Oh, sorry. There we go. So, run this from the canvas. Now, one of the cool things about in-order traversal is it gets its name by the fact that it prints out the values in order, as in ascending order. So I'm going to let this populate. We'll let this finish. Print in order. Okay? Now, for the sake of time, what should be the first thing that gets printed out?
Oh, yeah.
remember, the order is left subtree, root, right subtree. So it should go left subtree, left subtree, left subtree, left subtree, left subtree, until what happens? Yeah, until there's not a left subtree. And then it prints out the root. And then it prints out the right subtree. So what should happen is, we call print pre-order, print in order, excuse me. Okay. Is there a subroot? Yes. So go down to the left. 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 So we get the left child. Hey, there's no left child. There's no left child of 1,000. So what do? Print out the root, which is 1,000. Is there a right child of 1,000? No. So we go back to where the subroot was 1,001. At this point, we printed out the left. Now we print out the root, which is 1,001. Done. Now we go right, because we've done the left, and we've done the root, now we do the right, which is 1,003. We go left, there is no left, so we print out the root, and we print out the right, there is no right, then we return back to 1,004, print out that, and let the process continue. So if we've done in order correctly, this should be in ascending order. 1,000, 1,001, 1,003, 1,004, 1,005, 1,007, 9, 9, 11. 1,018. That was really easy, wasn't it? We just switched 2 months ago. I bet you guys could probably figure out the third traversal time. Probably going to be in it. Question?
This is going to sound down, but post order is pretty much descending order, right?
Yeah.
Okay.
So, we'll close out of this. I will let me uncomment this stuff. And I will put it as is on Canvas for you guys. There's a version up there on Canvas now. I'm going to override that with what we did today so you guys have a reference for creating your traversals. Now, what questions can I answer for you guys about your programs? Yes?
When I asked you about the compare to for the words, but for the strings, when it's already added in the tree, how do we do we have to specifically make a condition to check if it's already in the tree? And
Yes.
if it is, then just add frequency?
Correct. So let me explain how you do this, okay? If you look at the code, specifically, look at this. This is the line of code that actually passes to the insert method the word that you're to add. Now you notice it passes it as a string. So in your binary search tree class, you need to create an insert method that accepts a string. Now, the first thing you should do is you take that string and you search your binary search tree. Okay? Now, your binary search tree is not made up of strings, it's made up of node objects. Your node objects contain a string, a frequency represents the number of times that string appears in the tree, a left child and a right child reference. Now, you pass the string to the insert method. The first thing you do is you search the entire tree, checking to see if that string is contained inside of any node objects already.
Can you say that one more time?
Sure. You take the string that you're adding and you check to see if that string already exists in any node object in the tree. So for example, let's say you get the word pi. You're passing the word pi to your binary search string, right here. Insert. Before you create a node object. Before you add that node object to the tree, the first thing you do is you search the tree, and you check every node in the tree, and you check to see if any of the nodes in the tree already have a word that matches pi. Okay? Are there any node objects that have the word pi in them? Does that make sense? You guys are all on the same page? Okay. Now, one of two things will happen. If a node already exists in the tree with the same word that you're trying to add, you simply find that node in the tree, and typically your search method should return a reference to the node object if you find it. Take that node object and increase its frequency by 1. Okay? So if we go to add the word pi to the tree, and we're searching through, and we find a node object that has the word pi as its word, we simply increase the frequency of that node object. We do not re-add it to the tree. We don't have two separate nodes that both have the word pi. Okay? Now, the other thing that could happen is you search the tree, and you don't find a node object that has pi as its word. At that point in time, you will then create a node object, setting its frequency to 1 and setting its word to whatever word we pass it. And in our example, we're passing in pi. So we'll set its word to pi and we'll set its frequency to 1 because it appears 1 time in the tree. We will then take that and add it to the tree. Okay? Does that process make sense? Yeah, you should not have more than one word. You should not have duplicate word entries into the tree. So at most, there are 15 words, right? I think there are 15 words. You should not have more than 15 node objects in your tree. I think there are 15 words. 1, 2, 3, 4. 16 words. You should not have more than 16 words. Nodes. That makes sense. Again, do not add strings to the tree. Take the string, put it in a node object, along with the frequency, a left child or right child reference. That's for sure. The way you compare strings is they should be compared alphabetically. So if we ran print in order, it should print out the words alphabetically. The way you handle that in code is you use the built-in string class compare to method. It's there for you. It will automatically compare strings alphabetically. Okay, use that as your basis for going left or right down your tree. All right, what other questions do you guys have that I can answer? Yes?
Regarding the compare to method, while testing with the numbers, it appears that the compare to method only looks at the string in order of characters. So when comparing the number 11 to 9, it thinks that the number 9 is greater than 11. So is there a way to work around that, or do we just accept it because we're doing it with strings and not integers?
Don't, because when we grade it, we're going to use a default one that is going to use the words. If you're gonna do, what we really should do is put 0, 1, 0, 2, 0, 3, 0. Just change it like that locally on your end.
I thought I was going crazy when my tree was putting stuff in random spots.
Right. But you're absolutely right. I mean, when you're talking about the algorithm for alphabetical sorting, it goes character by character. So
Okay.
that's going to happen.
One thing I was just noticing when I implemented all the search orders is it does the words just fine and does the frequencies just fine and searches them. But when I do the print post order, it gives the exact same result for all three.
Look at your code for your traversal methods and make sure it's not the same. So for example, if you look at ours, here's our print pre-order, here's our print in order. Notice this one we do left subtree, print, right subtree, and this one it's print, left subtree, right subtree. Make sure they're not the same.
They're different. My only difference is I used a getter for the word as opposed to a two-string.
Are you outputting the word? I'd have to look at your code. Just off the top of my head, that's the best I got. Other questions?